These next couple of units are kind of put in here as an introduction to some college courses, especially if you're planning to go on to a nursing degree, ADN program. The chances are you're going to end up going on for a 4-year degree eventually. Right now, I'm not exactly sure where the laws are sitting, but I know that the talk has been there for a couple of years that all nursing careers, to be certified, you're going to end up having to get a 4-year degree eventually. So one of the steps you would have to take, the requirements in a 4-year degree, there'll be 2 of them, math-wise at least. It'll be either college algebra, or most colleges allow you to do a first semester of calculus in lieu of that, which very different level courses. The college algebra is a lot easier, but kind of assess the same competencies. And then a statistics course. Any medical related degree is going to require statistics. So for the next couple of weeks, we're going to focus on the college algebra. We're going to have, I believe, five lectures on college algebra, 5 or 6. Then we'll have our algebra test. And then we're going to spend about 3 or 4 lectures on statistics, and we'll have that test, and that'll bring us to the end of the semester. So we're not trying to cover these topics in great depth, but we're trying to give you enough of an introduction so that if you do go on to those college level courses, you have that background and you're ready to hit the ground running. By the way, statistics, I believe would be one of the most important classes you could ever take in a college degree. Unfortunately, most first semester introductory statistics classes become very mechanical. They teach you more of what you need to do to survive the course than what you really need to do to understand the material. Mainly because it is a very tough topic and has developed kind of a bad reputation as being a difficult class. And because of that, they've kind of watered it down and oversimplified it in many cases where it's mechanical and you really don't understand what's going on. But statistics is really just a study of decision making and analyzing information and making information-based decisions. And we'll hit on some of that, but by no means will we get in much depth at all on it. But hopefully I'll be able to give you some background that'll give you a little bit more insight to how those work. So anyway, today then we're going to start on the college algebra side of things. And we had some algebra at the beginning of the course with dealing with algebraic numbers and solving equations. So today we're going to look at it more from the geometry side of it. And what we're looking at is relationships between numbers. In mathematics, we have what's called mathematical relations. And a relation is just 2 sets of numbers that have a link between them. For example, we might have 3, 7, and 15 in one set of numbers. And in a second set of numbers, we might have 2, 12, and 35. And it might be that 3 in this relation becomes 12, 7 becomes 35, and 15 becomes 2. The relation is nothing more than a connection, like I said, between 2 sets of numbers. We have a first number that's often considered an input number, and a second number is often considered like an output number. We're not going to take the time in this course to get into all of the different ways of expressing the relation, and we're not going to get into the distinction between a relation and a function, which is a special type of relation. But we are going to talk about some of the ways of displaying these pairs of numbers that are paired together. Whether it's displayed like this, what we just showed you here is what's called a mapping, by the way, where we have one set of numbers and then we have arrows that map or connect those numbers to the other set. And this is a one-to-one mapping where each number goes to exactly one number in the other set. Again, we're not going to talk too much about those special qualifications. These numbers could have been displayed in a table where we had the input And for lack of a better term right now, I'm just going to call the input x and the output y, because that's typically the variables we associate with them. If we were certifying that this was a function, we would have terms like domain and range that we're not going to get into. But we could display this as 3, 7, and 15. Thanks, Brett. The 3 becomes 12, the 7 becomes 35, and the 15 becomes 2. No matter how we display them, these numbers are linked together, and it's what we call an ordered pair. So this first one here, 3 and 12, make an ordered pair like this, 3 comma 12, and usually put in parentheses to distinguish that it is an ordered pair. We had used the terminology a little bit ago of input and output, that this first number is the input and the second number is the output. And if we were doing like a regression analysis, finding an equation or whatever, that would be exactly how it worked. More common terminology is independent and dependent variables. And what that means is the independent variable is usually a number that can change and vary in value however we want it to within a certain range of possibilities. The dependent variable is the one that generally changes because of the changes we've made to the first variable. Therefore, it's often thought of as kind of like a cause and effect. So changes to that independent variable cause the changes in the dependent variable in some cases. Now that we can't necessarily make that assumption, often the changes that appear to be linked together like that cause effect might be because there's a third factor that's changing both of them at the same time. So we have to be a little bit careful about that terminology. We can't always assume a cause-effect relationship between them, but they do change. Their values do change on some sort of a set basis. So anyway, we want to be able to display these ordered pairs graphically. If you recall back to the first weeks of the course, especially when we were working with negative numbers, integers, we talked about a number line. And a number line is often used to display the value or the magnitude of a single number graphically. And there are a couple of different ways that we can display a number on the graph. The way that we used earlier when we were doing integers, dealing with those negative numbers, is we used a vector notation. If I wanted to display the number 6, I did a vector that started at 0 and went to 6. And that's what we used for calculating with those integers. And that's a great working display for using in calculation. If we're going to use that number for anything, that's the preferable method of displaying it. However, if we're going to display a lot of values on the graph, other than just single ones or a few that we're going to be combining with addition or subtraction, it's simpler to just display it represented by a simple dot. That dot at the number 6 means there's a number 6. If I needed to display several values, like 6, 2, negative 3, 7, negative 5, 3, 1, 6, 4, negative 1. Well, I would display those 2. There's a dot here at 2, negative 3, dot at negative 3, 7 is right there, negative 5 is down here, positive 3. Now 6 here, there's already a dot at 6, I'd put a dot above it, 4, negative 1, and all these dots appear on this graph, on this number line, representing those individual values, and we can tell very quickly which ones are represented more than once, because the dots stack up like that. This also becomes relevant in statistics, by the way, as something called a dot plot, where we can display the frequency of data and a distribution of data very quickly. So that works great if we have a single number that we want to represent, but if we have a pair of numbers, back to that ordered pair. So let's say I want to represent the pair of numbers 3, 7. Now you might think it would be easy enough to represent those two numbers on the graph and connect them. But you've got to remember, not only do we have to represent the 3 and the 7, but we have to represent that they're connected. We could do some sort of a curve connecting them, but then we have to remember we still have to represent the order. We have to represent that it is 3 and then 7, because that's a very different ordered pair than if it was 7 and then 3. So I don't know if we'd have an arrow or whatever, but if we did this, you could see that this number line would get cluttered very quickly, and it could be very confusing as the numbers overlap, trying to decide where's the arrow or what's this line overlap. So a couple thousand years ago, a man by the name of René Descartes came up with a solution for this. And what Descartes came up with was, we're going to start with a number line. Just like any other number line. And we're going to label that the x-axis or the independent axis. And then we're going to take a second number line, and we're going to start it at the 0 of this number line, and we're going to go vertically instead of horizontally. So the 0 of that second number line is going to be at the 0 of the first one. And we're going to number positives going up now instead of to the right. And negatives going down now instead of to the left. And so for that number 3, 7, that ordered pair 3, 7, we need to represent the 3 is on the independent axis. Of course, the vertical one would be the y-axis or the dependent axis. So anyway, now the 3 would be the x value or the independent axis. Here's 3 on the x-axis. The 7 would be the y value or the dependent axis. That's up here. To represent the two of them together, they project that out into space, and they put one dot right there. Think of it as like its shadow falls straight down on 3 on the x-axis and over on 7 on the y-axis. So if I give you a point right here, what is the coordinate of that point? What's its x-coordinate going to be? 6 and 2. Very good. Because it goes 6 on the x-axis and 2 on the y-axis. How about here? What's the coordinate of that point going to be? -3, 4. Wonderful. And how about this one? 1, -7. And this one? Perfect. So we can graph those points rather quickly. For ease of reference, our graph is divided up into 4 sections that are named. The 4 sections just come naturally from the 2 axes. 2 lines cut any plane into 4 sections. We label them here. This is what's called the first quadrant, because it's a quarter of the graph. Then it makes sense because that's where both the dependent and independent values are positive. So most sets of data, both variables are positive. So that's the first section of the graph that's usually used. From there, it's kind of subjective as to whether this would be the second quadrant or this one up here would be the second quadrant. And what we've done is in navigation and other things in trigonometry, everything goes counterclockwise. So we stayed consistent with that. This is the second quadrant, third quadrant, and fourth quadrant of the graph. And I'm assuming you guys all remember your Roman numerals to recognize those symbols. And then, of course, where it all comes together in the middle here, where the two axes cross, and where the four quadrants all come together, that is called the origin. That's where everything in the graph originates. That's 0, 0. Every numbering builds up from that point on the graph. So once we plot points on that graph, we need to look then, okay, why would we need to plot points on there? What would we track? And there are a lot of things data-wise that we would track, and we'll discuss that more in the next couple of classes. For right now, let's look at it algebraically. And we have solved equations like 3x plus 5 equals 14. How did we solve that equation? What's our first step? Subtract 5, good. So 9 equals 3x. And then divide by 3. So 3 equals x. We might have an equation 20 equals 3x plus 5. Well, we look at that because of the way it's structured. This side over here is exactly the same as this side over here. When we ask our questions about solving the equation, remember we found the equal sign, and then we identified which side has the variable on it, and we ask what's keeping it from being by itself, and then how do we get rid of it. Both of these, the variable, the x, has been multiplied by 3, and then 5 has been added to it. So the process of getting rid of all that is exactly the same. To solve this equation, just like we did over here, we would subtract 5. So 15 equals 3x. And then divide by 3. So 5 equals x. The exact same process of solving the equation, but because this initial number was different, the solution, the value of x, was different. We might have 8 equals 3x plus 5. Once again, we see that this side of the equation is exactly the same. So the process for solving will be exactly the same. We subtract the 5, 3 equals 3x, and then divide by 3. 1 equals x. Well, what we have up here is a family of equations. They all have the same basic structure here around our variable. It's just the number on the other side of the equation is different. I can describe all of those equations and anything else that's in that same family by replacing this number here that changed with a second variable. So y equals 3x plus 5. And this represents all of those equations I just put up there and more. Any equation that's of this form, 3x plus 5 equals a number. And I can now solve all of those equations in that family at once, and I can display those solutions. Well, displaying the problem is displaying those solutions could be, could be very tedious because there are an infinite number of them. What that means is for any number you can imagine for y, we can find a value for x that makes it true. And the other way around, any value you find for x, we can find a number for y that makes it true. Now up here, we were putting numbers in the position where the y is, and we were solving to find x. which works just fine. But it's a lot simpler if I put values in for x and found y. For example, if x equals 7, I find that y equals 3, instead of times x, it's 3 times 7 plus 5. And now it's just an order of operations problem. 3 times 7 is 21. 21 plus 5 is 26. So y equals 26. So that actually produces a solution to this equation. One solution to that equation is x equals 7 and y equals 26. Now again, that's an ordered pair. And as you mentioned, there's an infinite number of ordered pairs that make that equation true. So to display them, we use this graph. So I might take my y equals 3x plus 5. And plot it on this graph. I'm probably going to run into trouble here because I only numbered up to 7 each way, but let's see how it goes. Now I could do either way here. I could pick values for y and figure out what x had to be, or I could pick values for x and figure out what y has to be. But because this is y equals 3x plus 5, it's simpler if I pick values for x and put those numbers in for x and then figure out y, because it's just order of operations. If I put values in for y, I'd have to solve the equation. So for x, I'm just going to try different values. I want to take numbers that go all the way across. This is my x-axis right here. So I want numbers that some of them that are over on the left side, some of them in the middle, and some of them over on the right side of the graph. So I want the x values scattered out is basically what I'm saying. So I might do x is -2, 0, 1, and 3. That gives me a nice little spread across the graph. Now the first question that usually comes up, where did these numbers come from? The honest answer is I just flat out made them up. I just picked numbers that are scattered across the graph. You might have picked -3, -1, 2, and 5. Whatever numbers you want to try. Now I usually pick numbers that are closer to the center here, closer to 0, because they're less likely to get ridiculously high values for y so that they don't fit on the graph. There's at least one of these that's going to do that as it is. So then we're going to figure out what y equals. Y, remember though, is 3 times x plus 5. So if x is -2, y is 3 times -2 plus 5. What is 3 times -2? -6. -6 plus 5? -1. So this is giving us when x is -2, y is -1. So that's the ordered pair. So -2, -1 is right there. So next, if x is 0, y is 3x, so 3 times 0 plus 5. This one's an easy one. What's 3 times 0 plus 5? 5. So when x is 0, y is 5. So x is 0 right here, y is 5 is right there. X is 1, so y is 3 times x, so it's 3 times 1 plus 5. 3 times 1 is 3 plus 5, 8. So we have the ordered pair 1, 8. So 1 for x up to 8 for y. Now this next one is, like I said, we're going to go way off the graph. Let's try it. 3 times x becomes 3 times 3 plus 5. 3 times 3 is 9. 3 times 3 is 9, plus 5 is 14. Well, 3 is right here. That's okay, but I'd have to go up. 14 is going to be off the top of this graph. Somewhere up in here would be 14. So that point doesn't do us any good. We get that ordered pair 3, 14, but it doesn't do us any good because it's off our graph. So we look at the graph here and we decide, well, where can we pick more points? You know, just because we picked these points here to start with doesn't mean we figure out what the y value is for each of those points when we're done. We may have to figure out more points once we've got them on the graph to fill in to show us the rest of the picture. Now, right now, these 3 that I have appear to be in a perfect line, but it'd be nice to have a couple more points to be sure. So I'm looking at this seeing, well, I've got -1 here for x. I know there's going to be a point in there somewhere maybe. And then let's go to maybe -3 for x and see what values we get. So if x is -3, y is 3, or sorry, if x is -1, y is 3 times -1 plus 5. I wrote -3 in there again. So what is 3 times -1? -3. -3 plus 5. -3 plus 5 is 2. So with the ordered pair -1, 2. So -1 and 2 is right there. It's still looking pretty good for our line. If my graph had been perfectly straight, it looks like that is a straight line. -3 just to be sure. So 3 times -3 plus 5 will give us y. 3 times -3 is -9. -9 plus 5 is -4. So we have the ordered pair -3, -4. So -3, -4 is right there. And that should seal it for us. But yes, this is a perfectly straight line across our graph. So I can connect the dots and draw that line through those dots. So I'm going to stop for a second here and talk about that line. What does that line truly represent? I mean, it goes through all these dots that we put on here that are solutions to that equation. They're ordered pairs that are solutions to that equation. But the line's more powerful than that because every point on that line is a solution to that equation. The point here, where x is 0.4, if I take that point and I trace it down to x being 0.4, that's my x value. If I trace it over here, oops, should actually come right up here, I get y is 6.2. That's an ordered pair. X is 0.4, y is 6.2. That should be a solution to this equation. Or I could pick an x value. Let's say I want to know x is a -0.5. Well, I go to -0.5, I trace that up to my line. Once I hit the line, I trace that over to the y-axis. So this was a -0.5. This here comes out on the y-axis at 3.5. So that coordinate there, that ordered pair of -0.5, 3.5, again, that is a solution to that equation. That pair of values for those variables will make that equation true. And I can do that with any point on this graph. Now, not all graphs, not all equations will produce a straight line. We might have one like this. Y equals x squared plus 2x plus 15. I'm actually going to move down to the next page here so I don't get cut off by the end of the page. So we're looking to graph this again. And once again, I'm going to make a table, and I'm going to pick values for x, and I'm going to calculate to see what y has to be. So you can see here, this kind of shows you why this is called the independent and dependent variable. I am picking whatever variables, or whatever values I want to try for x, and then I'm using them to figure out what the y has to be here. So the value of y that I get over here depends on what value I chose for x over here. So for x, let's pick some pretty simple values. I'm going to pick them close to the center. I'm just going to pick a few of them here. I'm going to go -2, 0, and +3. So I'm just going to use the 3 of them for now. I'm going to start out with a -2. I'm actually going to give myself a little more room here for the 0. Start out with a -2. I replace x here with -2. Remember, this is y equals x squared plus 2x minus 15. So -2 goes in for x. That becomes -2 squared plus 2 times -2 minus 15. Be a little bit careful here with your calculators because, as we've mentioned before, many of your calculators, when you go to square a negative, if you're not careful, will give you a wrong answer. What is -2 squared? -2 squared is -2 times -2 is 4. +4. If you enter that in your calculator incorrectly, if you do -2 squared like that, it'll try to tell you -4 because it's not squaring the negative. You have to put it in parentheses in your calculator. -2 in parentheses, and then square it to make it work properly. So that's 4. 2 times a -2 here is a -4 minus 15. So what we have, 4 plus -4 is how much? 0. And 0 minus 15? -15. Good. So we get an ordered pair, -2, -15. So -2, -15. We can see that's off the bottom of our graph considerably, so that's not a terribly useful point. If we do 0, so we've got 0 squared plus 2 times 0 minus 15. Well, this one's pretty simple. 0 squared is 0. 2 times 0 is 0. So we've got 0 plus 0 minus 15, which is -15. Perfect. Thank you. So we got 0, -15 as a point there. Well, once again, that's not a horribly useful point. 0, -15 is going to be down here off the graph. So let's try 3. So we've got 3 squared plus 2 times 3 minus 15. What is 3 squared? 9. What is 2 times 3? 6. So 9 plus 6 is 15. Minus 15 is 0. So we get the ordered pair 3, 0. There's one that fits on a graph right there. Well, so far, we have these points way down here that are way off our graph, and one that's where it's useful. Now, the first thing I can draw from the points I have here, this definitely does not look like it's going to be a line. Second thing I can draw is I need more information, probably in here somewhere, the negative or +1, +2 range, and maybe -1, -3. So let's try that. First of all, let's try +1. See what that gives us. So 1 squared plus 2 times 1 minus 15. What is 1 squared? 1. 2 times 1? 2. Good. 1 plus 2 is 3 minus 15 is Negative 12. So with the ordered pair 1, negative 12. So positive 1, negative 12 is somewhere in there. Again, not a horribly useful point. So it looks like 2. Good call. So we'll try 2. So 2 squared plus 2 times 2 minus 15. So what is 2 squared? 4. 2 times 2? 4. 4 plus 4 is 8 minus 15? Negative 7. So that gives us that ordered pair 2, negative 7. That one's at least going to be on a graph, right in there. So we're seeing right now, it looks like this comes down here somehow. Not totally sure how it gets from there to this point. So let's do negative 1, even though it's going to be off our graph. Let's do it and see what we find out. So negative 1, we're going to have negative 1 squared plus 2 times negative 1 minus 15. What's negative 1 squared? 1. 2 times negative 1? Negative 2. What is 1 plus negative 2? Negative 1 minus 15 is negative 16. So we get negative 1, negative 16. That didn't go down too much further. You know, here's negative 1. This was negative 15 here, so negative 16 is somewhere in there. So it looks like it might hit that point and curve back up. So let's see what happens over here at like negative 3, negative 4. So let's try x equals negative 3. So negative 3 squared plus 2 times negative 3 minus 15. What is negative 3 squared? 9, good. 2 times negative 3? Negative 6. Now I've got 9 plus negative 6. Careful. Positive 3, yeah, good. Positive 9, negative 6 is going to stay on the positive side. So then 3 minus 15 is negative 12. So the ordered pair negative 3, negative 12. So there's negative 3, negative 12 somewhere down in here. So yes, it does appear that this is going to curve. And I could take more points on the left here, but to be honest, I'm getting a little tired of this problem. So there we go. This is what's called a parabola. And it has the exact same properties as the line, other than not being straight. Any point I pick on that parabola is a solution. Like this point here is somewhere between negative 4 and negative 5 for x. It looks like it's somewhere around negative 4, negative 3 to negative 4 for y. Every point on there, if I can find its precise x and y coordinates, will be an ordered pair that's a solution to that equation. So there has to be an easier way of graphing than doing out these tables. Unfortunately, math is about patterns. So to find those methods, we need to come up with patterns. Now I don't have it, I didn't send it out to be printed. I put it on Blackboard for you so that you can download it at home or do it electronically if you want to. You do not have to submit this. This is just a homework assignment. We're going to do a couple of them together here with the time we have left. And then the homework will be the rest of this. But on Blackboard for this course, if you look in course information where all the recordings are, and go all the way down to the bottom, right to the bottom of this worksheet. I did put the solutions out there in case you get stumped. You can look at them. But it's a graphing worksheet. And what we're doing on this worksheet is we are looking at plotting points and figuring out what the graphs look like. Now I did put some values in here to use for x. those may or may not be enough to get a good picture of the graph. Some of those values for x may give you y values that are way off the graph. Or they might give you y values that are ugly decimals that don't work so well. Down here, I tried to give you some that'll work out nice because we're dealing with a square root. And several of these, the values I gave you will not be enough. You'll have to choose more values in order to get a good picture of what the graph looks like. I want to do number 4 with you here, just because it's kind of a different problem, and it introduces us to a concept I'd like to talk about. So for number 4, y equals the square root of x plus 6. So if y, give you here that y could be negative 6, or we're going to try y as negative 6. I'm going to zoom in on this a little bit more. There we go, a little bit bigger to look at. So if y equals negative 6, or x equals negative 6, y is going to be the square root of negative 6 plus 6. Well, what is negative 6 plus 6? Well, negative 6 plus 6 would be 0. What's the square root of 0? 0. So that gives us the ordered pair negative 6, 0. So negative 6, 0, we're right there. If x is negative 5, y is negative 5 plus 6, then square rooted. What is negative 5 plus 6? Negative 5, positive 6 is 1. Positive 1. And the square root of 1 is 1. So that gives us the ordered pair negative 5, 1. So negative 5, 1 is right there. If x is negative 2, y becomes negative 2 plus 6 in the square root. What's negative 2 plus 6? 4, right? What's the square root of 4? Square root of 4 is 2. Good. So that gives us the point negative 2, positive 2 is right there. Well, we can already see this is not going to be a line either. If x is 3, y is the square root of 3 plus 6. What's 3 plus 6? 3 plus 6 is 9, and square root of 9 would be 3. So this is at 3, 3. And at 10, x is 10, y is going to be the square root of 10 plus 6. 10 plus 6 is 16. Square root of 16 is 4. So that's the ordered pair 10, 4. It's going to be over here slightly. Now when I graph this, I'm going to graph it like this. You'll notice I put an arrow on this end of it, but not on this end here. The reason for that is this end cannot keep going. It must stop there. If I put in negative 7 for x, that would make y would be negative 7 plus 6 and then square rooted. Negative 7 plus 6 is negative 1. If I try to do the square root of 1 on my calculator, what's it going to tell me? Either it'll say error or domain error, depending on the type of calculator you have. That's because, I mean, we could get into abstract algebra with imaginary numbers and stuff. But with hard real algebra, we can't take the square root of negative 1. We're not going to talk about I or imaginary numbers. So that can't be done. So negative 6 is the smallest number we can put in for x and make this still possible. If we go smaller, we're square rooting a negative. It's not possible. So that's a limit on this equation, this graph. It cannot go past that point. We'll talk about more of those limits next class. For now, work over the weekend until next Wednesday. Please work on this worksheet. Next Wednesday, we'll actually go through and we'll make sure we graph all of these. And then we'll go from there. So you guys have a great weekend, have a good holiday, and we'll see you next Wednesday.